Alright, a really common application of differential equations is in the world of physics to measure the positions and velocities and accelerations of things and to solve problems that involve those ideas. Okay, so you've got to understand the relationship between them, and it's really pretty simple. Let me map it out for you. We'll just start with the notation. We'll let x of t represent an object's position, v of t its velocity, and a of t its acceleration. Well, the way differential calculus or differential equations come in is that velocity happens to be the time derivative of position. So if you take position and you differentiate it, you get velocity. If you take velocity and you differentiate it, you get acceleration. So acceleration is dv dt, which is the same as d squared x dt squared. You can also think of going backwards. So if you have acceleration and you want to get an object's velocity, you have to go this way, which means you have to integrate. And if you have velocity and you want position, well, you have to go this way again and integrate once more. And in addition to these facts, there's one other fact that's helpful to know, because sometimes these problems involve acceleration and velocity and position in the vertical direction on Earth when there's gravity. So it's really helpful to know the following. The acceleration due to gravity on Earth is 9.8 meters per second squared, or 32 feet per second squared. And really any position, velocity, acceleration problem basically amounts to using these facts and your word problem translation skills and then some integration. So let's do one example of this. Alright, so suppose you're on top of the tallest building in the world, which is the Burj Khalifa in Dubai. And so you're up there at 830 meters, you let go of a ball from rest, and you ask yourself, how long does it take to fall and hit the ground? Well, here's how we do it. We know that its acceleration is the acceleration due to gravity, so that's 9.8 meters per second squared, and we're going to let negative quantities correspond to downward things. So here's the translation of this problem into a differential equations framework. d squared x dt squared is the expression for acceleration when x is the ball's position. So the acceleration is negative 9.8, the acceleration due to gravity. X at time 0 is 830 meters because we're on top of the building, and x prime at 0, that's dx dt at time equals 0. That means the ball's initial velocity is 0 because we just let go of it from rest. We don't throw it down, we simply release it. So you look at this problem, you realize that you can solve it by direct integration, and we get the following. You get dx dt equals negative 9.8 t plus c1, and that's just, again, from direct integration, and c1 is the constant of integration. And we can now use one of our initial conditions, x prime at 0 equals 0. Well, that means, substituting directly, that c1 has to be 0, so this goes away. Okay, now to get x, we have to integrate one more time. We get negative 4.9 t squared plus another constant of integration, and we know that x at 0 equals 830 meters, the initial height of the ball. And so if you substitute, that tells you that c2 has to be 830. Therefore, x of t is negative 4.9 t squared plus 830. Now we want to find how long the ball takes to hit the ground. Well, when it hits the ground, its position is 0, right? So we're measuring the ground as the reference point, x equals 0. So we can do something like this. If we let t sub imp be the time to impact, the time to hitting the ground, we know that x of t imp is negative 4.9 t imp squared plus 830, that's from above, and we set it equal to 0 because we want to solve for the time at which the position is 0. So then all you have to do is isolate t imp, you bring one term on the other side, you divide by 4.9 and you take the square root, and you find that time to impact is approximately 13 seconds. Alright, that's it.